Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Let's repeat the example that we went through in the overview video about calculating torque, but this time using vector notation. So, first of all, we have the vector f, and it's at 30-degree angle relative to the axis of the rod. So let's complete the vector diagram. So we have, this is the vector r that indicates the location where the force acts measured from the pivot point. And we are trying to calculate the torque in a vector form, which is the cross product between the r vector and the f vector. To do this, we need to be able to express these vectors with their components. So this is a 30-60 triangle. So if the length of this hypotenuse is f, then the short side is going to be half of that, half f, and the longer side would be square root of 3 over 2 times f. In this manner, we have the following vectors. So f is, so let's have our x coordinate system as follows. So x is along the length of the rod, and then y is perpendicular to it, like this. So f will be the x component square root of 3 over 2 f in the x direction unit vector I plus 1/2 f in the y direction unit vector j. And because the rod lies on the x-axis, it's just going to be, so if its length is L, the pivot, or the vector from the pivot point to the point where the force is acting is just L times I. Now we're ready to evaluate this cross product, and we do it using the matrix form or determinant form. So first of all, we list all the axes that we are playing with, so I, j, and k, x, y, z, and you'll notice why we have a z axis in just a minute. So, and then we, on the second row, we list the components of the first vector, that is r. So r was L times I, so it only has L here and nothing in the y and z directions. And then f has square root of 3 over 2 in the x direction, and well, that times f, and half times f in the j direction and or y direction, and nothing in the z either. And again, how do we calculate this determinant? So let's make our help signs here. So everything with I has to be added, anything with j will be subtracted. And then again we have plus for the k direction. So first we evaluate the I direction. What do we have there? To do that, we'll block this column and evaluate the determinant of these 4 elements. So that's going to be the diagonal sum minus the other diagonal, or diagonal product minus the other diagonal product. So 0 times 0. So I used colors, so 0 times 0 minus the other one, half times f minus 0. So we get nothing in the I direction. What about j direction? So first of all, look at this, we have to use minus j. And in this case, we block this column, the j column, and the top column again, and we'll calculate the diagonal product of the remainder, so L times 0 minus the other product, square root of 3 over 2f here times 0 there. So nothing in the j direction either. And then finally we have the k direction, so we block this column and this row, and now we should have something left. So let's make this clear. So we are only evaluating in this case now the determinant of these 4 elements. So in j direction we have positive, so k direction. So what do we get? L times half f minus square root of 3 over 2f times 0. So as you can see, all of these are zeros, so we only have contribution from the k direction. And to be exact, we have f times L divided by 2 and k. And this is important that we have the direction of the torque. And what does it mean? So it's pointing in the z direction. And to interpret that result, we use our right hand rule. So if we point our right hand thumb in the k direction, the curl of our fingers will signify the direction of the rotation. So let's draw that again. So if we had our r along the x-axis and then the f for somewhere in the xy plane, like this, and by taking the cross product of the two, the resulting vector is always perpendicular to the both, so hence we get the z direction for the torque. Again, if we point our thumb along the torque vector, the z direction, and we point our fingers, the remaining fingers, towards the r, and then curl our fingers towards f. Or we don't even have to think about the f, we just curl our fingers, and that will give us the direction of the ensuing rotation. And this of course makes sense that we have counterclockwise rotation when the f is directed, as we see in this figure. And from this vector we can of course calculate the magnitude of the torque, which is just the magnitude of the vector. So it's simply going to be FL divided by 2, and we had 10 newtons for the force, and the length of the rod is 1 meter. So, and that divided by 2, so the 5 Newton meters as we expected from the earlier calculation of this problem. What about the angular acceleration then? That is also a vector quantity, and if we backtrack a little, so this is the equivalent of Newton's second law in the rotational motion. So the sum of net torque about some axis is same as the moment of inertia times the angular acceleration, which is also a vector. So if we go and solve the angular acceleration, we get the net torque in the vector form divided by moment of inertia. And what is our net torque? Well, we only have this one torque, the tau vector we calculated, so that's going to be just FL divided by 2, and remember, in k direction. And then the moment of inertia for this rod is, as you might already remember, 1/3 mL squared. And we can simplify this, so these L's cancel, and we have 3/2. In the numerator we have F, and that divided by m times L, and all of it in k direction, so 3/2 times force Newton, or 10 newtons, divided by mass 2 kg times the length of the rod, 1 meter. So we get 15 divided by 2, so 7.5, and the units turn out to be 1/second squared, or 7.5 radians per second squared, and all of that again in k direction. So by starting from this vector notation and carrying it all the way over, we not only get the direction of the torque, but also the direction of the angular acceleration, and that as well obeys the right-hand rule. So if we point our thumb in the direction of this vector, which is k, the positive c direction, by curling our fingers, we get the direction of the accelerating rotation. So, and that is the bonus by going through the trouble of using vectors. You not only get the magnitude, but you also get the direction. And in general case, the forces are not usually given in the simple terms of direction. They might be in the vector form to start with, and then the vector notation and calculating the cross product using matrix form is the fastest way to solve the problem in the first place.